Lasers, an acronym for light amplification by stimulated emission of radiation, are devices that emit light through a process of optical amplification. Lasers are categorized according to various criteria, including the type of lacing medium, the wavelength or frequency of the emitted light, and their applications. One significant way to categorize lasers is by their frequencies, which correspond to the wavelengths of the light they emit. The frequency of a laser determines its energy and its potential uses. By understanding how lasers are categorized by frequency, we can gain insights into their diverse applications across different fields. Ultraviolet lasers emit light with wavelengths shorter than visible light, typically between 10 and 400 nanometers. These lasers operate at high frequencies and have high photon energy. Ultraviolet lasers are used in various applications due to their ability to induce photochemical reactions and their high precision in material processing. Common types of ultraviolet lasers include excimer lasers and frequency double diode pumped solid-state lasers. Applications of ultraviolet lasers range from medical procedures, such as eye surgery, to photolithography and semiconductor manufacturing and sterilization processes. Visible lasers emit light within the range of wavelengths that the human eye can detect, approximately 400 to 700 nanometers. These lasers are categorized into several colors, each corresponding to a specific range of wavelengths. Red lasers typically operate at wavelengths around 650 nanometers, green lasers at approximately 532 nanometers, and blue lasers at around 450 nanometers. Visible lasers are widely used in consumer electronics, laser pointers, display technology, and optical data storage. They are also used in scientific research, spectroscopy, and various forms of entertainment such as light shows. Infrared lasers emit light with wavelengths longer than visible light, typically between 700 nanometers and 1 millimeter. These lasers operate at lower frequencies and have lower photon energy compared to ultraviolet and visible lasers. Infrared lasers are divided into near-infrared 700 nanometers to 1.4 micrometers, mid-infrared 1.4 to 3 micrometers, and far-infrared 3 micrometers to 1 millimeter categories. Near-infrared lasers are commonly used in fiber optic communications, remote sensing, and medical diagnostics. Mid-infrared lasers are used in spectroscopy, environmental monitoring, and military applications such as infrared countermeasures. Far-infrared lasers, also known as terahertz lasers, are used in scientific research, security screening, and imaging applications. Terahertz lasers emit radiation with frequencies between 0.1 and 10 terahertz, corresponding to wavelengths between 30 micrometers and 3 millimeters. These lasers bridge the gap between microwave and infrared frequencies. Terahertz lasers are used in a variety of applications due to their ability to penetrate many materials without causing damage. They are used in spectroscopy, imaging, and communication technologies. Terahertz lasers are also employed in security screening to detect concealed weapons and explosives, as well as in non-destructive testing and quality control in manufacturing processes. Microwave lasers, also known as masers, emit radiation with frequencies in the microwave region of the electromagnetic spectrum, typically between 300 MHz and 300 GHz. Masers were the precursors to lasers and operate at much lower frequencies compared to optical lasers. They are used in applications requiring precise frequency standards, such as atomic clocks, deep space communication, and radio astronomy. Masers are also used in certain types of medical imaging and as low-noise amplifiers in microwave receivers. Radio frequency lasers operate at even lower frequencies, typically below 300 MHz. While true radio frequency lasers are rare, some specialized devices operate in this frequency range for niche applications. These include certain types of radar systems, communication technologies, and scientific research involving low-frequency electromagnetic waves. Radio frequency lasers are used in applications requiring long-range signal transmission and penetration through various media, such as water and soil. Each category of lasers has unique properties and applications, influenced by their frequency and corresponding wavelength. The energy of the photons emitted by the laser is directly proportional to its frequency, determining its interaction with different materials and its suitability for various uses. The higher the frequency, the higher the energy of the photons, which enables processes such as cutting, engraving, and inducing chemical reactions. Conversely, lower frequency lasers are used in applications requiring deep penetration, precise measurement, and communication over long distances. Ultraviolet lasers, with their high frequency and energy, are particularly suited for applications requiring high precision and minimal thermal impact. In the field of medicine, ultraviolet lasers are used for procedures like LASIK eye surgery, where precise removal of corneal tissue is necessary to correct vision. In manufacturing, ultraviolet lasers are used in photolithography to create intricate patterns on semiconductor wafers, a critical step in the production of microchips. The ability of ultraviolet lasers to break molecular bonds makes them effective in sterilization and disinfection processes, as well as in the synthesis of certain chemicals. Visible lasers, being within the range detectable by the human eye, are widely used in consumer and commercial applications. Red lasers, for example, are commonly used in barcode scanners, laser pointers, and optical disc drives. Green lasers, which are more visible to the human eye due to their wavelength, are used in applications requiring high visibility, such as laser light shows and surveying equipment. Blue lasers, with their shorter wavelength, are used in high-density data storage, such as Blu-ray discs, and in medical diagnostics for fluorescence microscopy. Infrared lasers, with their longer wavelengths and lower energy, are used in applications requiring deep penetration and minimal absorption by certain materials. Near-infrared lasers are essential in fiber optic communications, where they transmit data over long distances with minimal loss. These lasers are also used in medical diagnostics, such as optical coherence tomography, to create detailed images of internal tissues. Mid-infrared lasers are used in environmental monitoring to detect gases and pollutants, as well as in military applications for target designation and infrared countermeasures. Far-infrared lasers, or terahertz lasers, are used in imaging applications to detect hidden objects, in security screening to identify concealed threats, and in scientific research to study molecular vibrations and rotations. Terahertz lasers, with their unique ability to penetrate many materials without causing damage, are increasingly used in medical imaging, security screening, and quality control. In medical imaging, terahertz lasers can create detailed images of tissues without the ionizing radiation associated with X-rays. In security screening, they can detect concealed weapons and explosives without direct contact. In manufacturing, terahertz lasers are used for non-destructive testing to inspect the integrity of materials and detect defects. Microwave lasers, or masers, operate at much lower frequencies and are used in specialized applications requiring precise frequency standards and low noise amplification. Atomic clocks, which use masers, provide the most accurate timekeeping in the world, essential for global positioning systems and telecommunications. Masers are also used in deep space communication to receive faint signals from distant spacecraft and in radio astronomy to study celestial objects. In medical imaging, masers are used in certain types of magnetic resonance imaging to enhance signal clarity. Radio frequency lasers, while less common, have specialized uses in communication, radar, and scientific research. In radar systems, radio frequency lasers are used to detect and track objects over long distances. In communication technologies, they transmit signals over vast areas, penetrating various media. In scientific research, radio frequency lasers are used to study the properties of low-frequency electromagnetic waves and their interactions with different materials. In summary, lasers can be categorized according to their frequencies into ultraviolet, visible, infrared, terahertz, microwave, and radio frequency lasers. Each category has distinct properties and applications, influenced by the energy of the photons and the corresponding wavelength. From precise medical procedures and high-density data storage to deep space communication and security screening, lasers play a crucial role in various fields, demonstrating the remarkable versatility and potential of this technology. Understanding the frequency-based categorization of lasers provides insight into their diverse applications and the underlying principles that govern their interaction with matter.